All right, hey Global Impact students, this is Mr. Ellinger here, and this lesson is on quadratic functions and transformations. This is our first lesson in Unit 4. We're going to really dive into quadratic functions and do a lot of different things with them. This first lesson, our learning target is to identify and graph quadratic functions. Some essential understanding for you for the lesson. The graph of any quadratic function is a transformation of the graph of the parent quadratic function, y equals x squared. The vertex form of a quadratic function is f of x equals a times the quantity x minus h squared plus k, where a cannot equal 0. The axis of symmetry is a line that divides the parabola into two mirror images. The vertex of a parabola is hk, the intersection of the parabola and its axis of symmetry. So a parabola is what we call the shape of a quadratic function, the graph, okay? It's a U-shaped curve, and we can write the graph of a quadratic function in the form f of x equals ax squared plus bx plus c, where a cannot equal 0. Again, you're going to see this condition here of a cannot equal 0. And if you think about that, why would we need to put that on there? Well, if you take a look at the function itself, if a were 0, this coefficient right here were 0, then that would mean that this term would be 0. And if you say, well, so what? Well, if this was all 0, essentially this would be non-existent in our function, which would just leave us with a linear function. So we have to kind of put that condition on there when we look at the definition of a quadratic. So the graph of any quadratic function is a transformation of the graph of the parent quadratic function y equals x squared. The vertex form of a quadratic function is f of x equals this a times the quantity x minus h, all that quantity is squared, and then plus k, again a cannot equal 0. The axis of symmetry is a line that divides the parabola into two mirror images. The equation of the axis of symmetry is x equals h. The vertex of the parabola is hk. The intersection of the parabola and its axis of symmetry is where this thing called the vertex is. So let's look at a visual here of this. So here we have our parent quadratic function in blue. There's x squared. The graph is the parabola shown here. The axis of symmetry for this parent function is x equals 0, which is also known as the y-axis. And the vertex is 0, 0 right here where the parabola and the axis of symmetry intersect. Okay? So this mirror image concept, if I take a look at on both sides of the axis of symmetry, this thing is called symmetric. So basically what that means, if I were to take this left half of the parabola, fold it over the axis of symmetry, the left half would lay right on top of the right half. So we say that they're mirror images of each other over that axis of symmetry. Okay? And, the equation here, x equals 0, where that comes from is the x-coordinate of the vertex. X-coordinate of the vertex is 0. And we're talking about a vertical line, okay, that goes through that vertex. Vertical lines are x-only equations, okay, x-only equations. So that's why the axis of symmetry is always going to be x equals a number, and that number is just the x-coordinate of the vertex. All right, so let's take a look at an example here. What is the graph of f of x equals 1/2 x squared? So the steps that we're going to follow to graph this is, the first thing we're going to do is we're going to go ahead and plot the vertex. And for these are fairly simple quadratics. They don't have other terms. We only have our x squared term. So we can plot the vertex 0, 0 and draw the axis of symmetry at x equals 0, that vertical line. Then we're just going to pick some other points to plot, okay? So what we do is we make a table. And here's our vertex coordinate x, and when we substitute that into the function, we get a point 0, 0. When x is 2, we plug that value into the function. We get the value of 2 coming out of the function, so we have two 2's on our graph. And then we plug 4 in. Okay, this function evaluates to 8 when we plug 4 in, so we have 4, 8 on our graph. So what we do is we go ahead and plot those points. All right, so we have here's 0, 0, here's 2, 2. And here is 4, 8. And then what we do is we could go ahead and get these points here on the other side of the axis of symmetry, but we use this idea of symmetry. The point 2, 2 is 2 units away horizontally from the axis of symmetry. So Since we know this thing is symmetric, we just need to go 2 units on the other side of the axis of symmetry, horizontal, and we get another point on our graph. Same thing up here at 4, 8. 4, 8 is 4 units away from the axis of symmetry. So I just need to go 4 units on the other side of the axis of symmetry to get another point on the other side of the axis of symmetry that's on my parabola, okay? So this idea of symmetry on a parabola, on a quadratic function, gives us a way that we can develop a graph without having to put too many points on here, okay? If we don't use this idea of symmetry, then we would have to have more points in our table so we could really see the pattern and the shape of the parabola develop. And then finally, after we get those points, we would sketch the curve. The curve was already sketched here, so you could see I would get these points over here on the right side, and then I would use my concept of symmetry to get these points on the left side of the axis of symmetry, and then I would draw my curve through it. Remember, it is a U-shaped curve. Down here at the vertex is not a point, okay? It's a rounded bottom. Think of a U, okay? This is not an absolute value function, so we don't want to draw a point here. Definitely not a point, and that's going to be critical to draw these things correctly when we move on to calculus. Okay, so the graphs of y equals ax squared and y equals negative ax squared are what we call reflections of each other across the x-axis. Increasing the absolute value of a stretches the graph vertically and narrows it horizontally. Decreasing a compresses the graph vertically and widens it horizontally. Okay, so here we have a couple different graphs. Our first graph, we have the blue curve is x squared and the red curve is negative x squared. So you can see when we put this negative in front of x squared, we now get a reflection across the x-axis. The stretch concept here, if a is greater than 1, so say y equals 2x squared, then we get a graph that is narrower. Okay, so it stretches vertically and it narrows horizontally, meaning the y values are increasing at a faster rate as x increases than they are on the parent function. And then over here on our compression, if a is between 0 and 1, then this graph kind of widens out faster and it compresses vertically. So here you have y equals 1/2 x squared. The y values are not increasing as fast as they are on the parent function, so that gives us the compression look and widening out horizontally. Compared to the parent function, that's what we're always doing. We're comparing these back to the parent function. So if a is greater than 0, the parabola opens, we say it opens up, upward. The y-coordinate of the vertex is called the minimum value of the function. Okay, so we see that here. Here's an example of our parent function, y equals x squared. The vertex is what's called a minimum value. What that means is there are no y values less than that on this graph. It's the bottom one. It's the least value, the minimum value. And if a is less than 0, the y-coordinate of the vertex is the maximum value of the function. So we see that illustrated here in this graph on the right. If it opens downward, then the vertex is going to be what we call the maximum value. Okay, so here are a couple more examples. Graph each function. How is each graph a translation of f of x equals x squared, the parent function? In a, we have g of x. This function g of x equals x squared minus 5. So here's our red parent function, x squared. And then our blue graph is g of x equals x squared minus 5. And without making a table, if I understand what's going on here in terms of the translation of this function, I don't really need to make a table of values. I just need to understand that x squared minus 5 is going to be a vertical translation down 5 units. Okay, so I take the vertex, translate it down 5 units. I can take these other points and translate them down 5 units. So if I translate the points themselves, then I can draw the curve. So I get a translation of the graph that's down 5 units, the parent function. All right, in B, h of x equals the quantity x minus 4 squared. Well, we know that if I add or subtract a value within the function itself involving x, then I know that's going to be a horizontal translation of some kind. And I know that if I subtract values from x, then I'm going to translate this to the right. In this case, I'm going to be translating to the right 4 units. So red curve is my parent function, and the blue curve is my new function, h, translated to the right 4 units. And again, I would just go point by point I could translate the axis of symmetry if I wanted to see where that is, and then get some other points translated over to the right 4 units to see where my new function h is. So the vertex form, f of x equals a times the quantity x minus h squared plus k, gives you information about the graph of f without drawing the graph. If a is greater than 0, k is the minimum value of the function, okay, the translation part. If a is less than 0, then k is going to be the maximum value, okay? And that kind of makes sense because if it's a parabola that opens up, and we know that k, wherever k is, that's the vertical translation, that's where we get our maximum and minimum values, okay? So if there is no k value in our form, then we know that the minimum or the maximum value is going to be 0. And if k were -2, then the minimum or maximum is going to be -2, depending on whether our parabola opens up or down. Okay, so for y equals 3 times the quantity x minus 4 squared minus 2, what are the vertex, the axis of symmetry, the maximum or minimum value, and the domain and range? So step 1, we just want to kind of analyze our equation in terms of the vertex form. So we have a 3 in the a spot, we have a 4 in the h spot, and we have a -2 in the k spot. Okay, and again, I'm comparing it to the general vertex form. So we can identify from the form that the vertex is hk, which is 4, -2. The axis of symmetry is going to be an x-only equation, x equals h, that's x equals 4. Since a is greater than 0, a is 3, the parabola opens upward, and k equals -2 is the minimum value. So if a parabola opens up, it has a minimum value, and k is that minimum value. The domain on a quadratic function is always going to be all real numbers. There's no restriction on the value of x. So again, any quadratic function, there's never a restriction on x. But the range is always going to be dictated by the minimum or maximum value. All real numbers greater than or equal to -2 are the range, since the minimum value of the function is -2. Okay, so if the function has a minimum, then the range is all real numbers greater than or equal to that minimum. If the function has a maximum, then the range would be all real numbers less than or equal to that value. Right? So vertex form is nice. We can use vertex form of a quadratic function to transform the graph of the parent function. We can stretch or compress, we can reflect if we need to, and we can shift horizontally and vertically, and we can get all that information just from the vertex form. So compare this to a linear function. The nice form for quick graphing, getting all the information we need, is slope-intercept form, y equals mx plus b. It's kind of like that version of a quadratic here. Again, it's very useful for us. I hope you guys have a great day. We'll see you next time.